This morning is Noah Petro presenting on Lunar Orbiter's Cornerstone mission, a new era of lunar science.
All right. Well, thanks very much. Okay. So actually I amended the title because to be more inclusive of this community, but also to be more correct, it's a new era of lunar and solar system science. And I'll make the argument that the science that LRO does is obviously not only relevant to the moon, but also to all solar system objects, including the Earth. There was quite a lively discussion yesterday about the eclipse. This is an example of an LROC image of a past eclipse showing what they'll be able to see. This is basically the path of totality right here. When the eclipse happens, the Earth will be 366,000 kilometers from the moon, so average LROC pixel on the Earth will be about 3.6 kilometers by 3.6 kilometers. And we talked a bit about what would it take for folks to shine their iPhone lights in the sky. And I did a little calculation, because when Jack suggests doing a calculation, you best dang do it. And turns out that the average luminosity of one iPhone is about 10 lumens, and it would take about a lot of iPhones to come up with enough. That's a good way to ruin someone's enjoyment of the eclipse, is to shine it up. But basically, if you took the largest football stadium, American football stadium, Clive, and filled it with people a couple times over with multiple iPhones, you'd have a lot of crowded people with burned out iPhones. So I'd like to talk a little bit about the status of the mission. Quite simply, LRO is awesome. LRO is nominal. The instruments are nominal, showing no unexpected degradation over now the 8 years of the mission. The operations team and the instrument operations teams are all awesome as well. We've had a number of folks who have been either on the mission operations side or the instrument operations side who've been doing this now for 8 years. From the mission side, we've had folks who are active in building and testing the spacecraft who now cycled off to do other missions. But the benefit of having a really awesome mission, to use that word again, is that folks are always willing to come back when we have any kind of anomaly or any kind of question about spacecraft operations. So at Goddard, certainly, we pull on the wealth of knowledge that we have there from constructing the instrument, the spacecraft, as well as the instrument teams pulling on their teams. So we have just an amazing group of people who are incredibly dedicated to this mission. Just as a few quick updates, and I'll get into a little bit more detail, Mini-RF is collecting data once again using both the Arecibo and Goldstone antennas for both X and S-band radar data. LAMP late last year opened their Failsafe door to increase their signal to noise, so they're now collecting data in a new mode. And because we're in our now current 2-year extended mission, we're 42% of the way through our 2-year extended mission, which means it's time to start planning the next extended mission, of course. Although we may go on to a 3-year cadence, so we're eagerly waiting word whether or not we'll have to propose for another extension next year. One of the requirements or requests from the last senior review is that the instrument teams, that we adopt a more integrated approach at doing our science, which we had sort of been transitioning to, and so we're very happy to report that we've started holding a series of thematic focused workshops. These are topics that were identified in the senior review proposal as being key science questions going forward, whether it was looking into some of the discoveries of potentially young lunar volcanism, the sort of ongoing debate as to whether or not there's a diurnal hydrogen cycle, looking at the basin formation era and the stratigraphy of basins, ongoing processes in the formation and evolution of the lunar regolith. And so these focus workshops over the last 6 months have integrated folks from multiple instruments on LRO as well as members of the community outside of LRO. We also have identified 3 team members on various instruments who are now acting as sort of collaboration leads, theme leads for cross-team work. Kathleen Mant now at APL, leading our volatiles theme. Julie Stopar at the LPI, looking into volcanism and tectonism, and Paul Hain who's here looking at regolith processes. And so these, not only these theme leads, but these workshops are leading towards a more integrated approach from across our mission. Just a few items of note that I want to highlight, and Andrea talked a bit about these yesterday. The next PDS delivery is on September 15th. And you can set your calendar if the month is divisible by 3. That's when we're making our PDS deliveries. We've generated the largest volume of planetary data of any mission of all time, over 800 terabytes now. Of course, there's the Eclipse on August 21st, and if I have time, I'll show a few more follow-up slides based on our discussion yesterday following Andrea's presentation. October 16th is kind of a cool, will be a fun date. That's when we'll celebrate 100 lunations, 100 lunar days orbiting the moon, from when we started our science mission September 15th, 2009. So we're going to be just highlighting some of the cool science that's come out of the mission over 100 lunar days. The moon doesn't really care much about the length of time on the Earth, so we're marking 100 days at the moon. Just following that is International Observe the Moon Night on October 28th. And just as a call out to the community, AGU in Nolans this year has multiple sessions that will highlight and feature LRO science. And so we eagerly anticipate and look forward to submissions to those various sessions. A little talk about the orbit. Because I'm a Carly Peters student, I always show squiggly lines, but my squiggly lines have gone from spectra to orbital parameters. So LRO is now in this quasi-stable orbit with our periapsis, our low pass, over the South Pole. This plot shows the history of the periapsis and apoapsis over the history of the mission, starting from orbit insertion through commissioning to the start of our prime science phase in September of 2009, when we were in our 2-year, 50-kilometer circular orbit, which brought us close to the moon, but was very expensive in terms of fuel. So in late 2011, we went into this quasi-stable, and we call it quasi-stable because, as we show here, it actually evolves. And so we've stopped doing yearly burns, fuel burns, which eat up about 2 kilograms of fuel per burn. At this point, LRO has about we use 96.8% of our fuel. So the fuel gauge is on empty, but we are in this low, this very low fuel maintenance orbit. And so we could potentially stay in a configuration like this where we don't do any of the large burns, reserving fuel for momentum unloads and phasing maneuvers, potentially for as long as about 10 more years. That does not include any more of these burns. Now we're evaluating possible changes to our orbit for the next extended mission that may lower the periapsis once again or change the configuration, take our periapsis away from the South Pole. All of those are under consideration. I should also point out that when we started, we were passing directly over the South Pole. Our orbit inclination has now shifted, where we pass over about 87.5 degrees. So here in this plot, this Eye of Sauron plot here, you can see that we no longer pass directly over the South Pole and Shackleton Crater. We get this density coverage, however, over areas about, again, 3 degrees, 2.5 degrees away from the pole. That is a benefit to us. We had a real dense coverage over the South Pole, and so now our density of coverage is extending. You can imagine as the mission progresses, that sort of donut, that bald spot will grow, and the density of coverage will increase as well. So we're going to have this incredibly dense coverage immediately around the South Pole. And as long as we stay in this configuration, we won't be shifting the change in periapsis. That's extremely fuel, high usage of fuel to do that. So we'll get this really kind of free density increase. I talked a bit about the duration of LRO and how we're just after 8 years now of launch. Again, in September, we'll celebrate 100 lunations. And this is a plot that I've kind of thrown together showing the duration of either orbital or surface experiments in terms of number of lunations. And actually, next week, LRO will pass the Apollo 12 LSEP station in duration of operations. We're about 5 days away, I guess, from passing the 97.3 lunar days that LSEP 12 operated on. And again, in October, we'll pass 100 lunations. Now, you may think, well, what is that at all important? Well, basically, the value added in having a long duration lunar mission gives us new science, and that's why I claim or talk about this new era of lunar and planetary science. All of these measurements here, all of these discoveries are enabled by a long-lived lunar orbiting mission. We're able to now cross-compare LROC images from earlier in the mission to recently collected images to find surface changes. And so we just heard presentations about the search for near-Earth objects. Well, we're finding the result of near-Earth objects striking the lunar surface. This is a 38-meter diameter crater that was, the flash was observed by an observing station in Spain on September 11th, 2015, I think it was. The LOLA instrument has been able to measure solid body tides, shifting tides on the surface of the moon. LAMP, crater, LEND are measuring volatile transport across the surface. The Diviner instrument is building up an incredibly high-resolution temporal thermal map of the moon. While we've been at the moon, a number of other missions we've partnered with, whether it's LADI, GRAIL, of course LCROSS. The existing Artemis missions have all provided opportunities to cross-compare, cross-collaborate. This duration gives us a chance to adopt these new modes of operation for multiple instruments. I mentioned Mini-RF and LAMP. The crater instrument is now basically refining how they collect data in order to get some new insights into the volatile transport process on the moon. These all give us an opportunity also to make additional targeted measurements. LROC can make these beautiful high-resolution DEMs from multiple observations. Now, if we had stopped a mission earlier on, we would not be able to collect new ones. And so for targets of opportunity for future missions, we're able to actually collect high-resolution DEMs in support of those missions. And just talk a minute, we've got a number of resources and data products available in the various archives. Just released yesterday, the LROC team published a number of new shapefiles on their website, which are listed here. These are obviously wildly popular to use in GIS databases and in various research programs. Here's an example of just regional slope weather derived from the LOLA instrument, or even getting at higher resolution DEMs that the NAC camera can produce. This is an example of a slope map of the Apollo 17 landing site derived from a NAC DEM, all of which are available on the various team websites. Here's just an example of the LAMP instrument, the Failsafe door open mode. This is the predicted sort of increase in fidelity of the instrument. And here's actual data from before the opening and after, where now on individual data strips, we get what we've called, in homage to Carly, M-cubed style measurements, where each individual orbit gives us, or gives a LAMP team, data that can be used as opposed to having to integrate over multiple orbits. A paper that just came out and is in Icarus now is the spectacular result of years of work by the LROC team in mapping the distribution of titanium using the wide-angle camera, the sometimes forgotten camera as part of LROC. This paper is now available online, and I highlight the popular downloads website from the LROC page, where you can actually go and download the full global, or I'm sorry, 70 degrees north to 70 degrees south WAC multiband product. It's a glorious data set. Another paper of note recently is J.P. Williams' paper in Icarus, highlighting thermal property variations on the moon. This is data not derived from any other instrument than Diviner. This is all based on thermal variations of the surface weather due to rock abundances around large impact craters. It uses the brightness from channel 1 of the Diviner instrument and the minimum and maximum surface temperatures to derive yet another way to gain insight into the lunar surface. It's a really spectacular paper, and again, the result of many, many years of observations. This is another result that came out in a paper published by the LEND team, looking at the distribution of hydrogen, or weight equivalent hydrogen near the South Pole. This is in a paper by Anton Sanin in Icarus as well. And so these map products are available as part of that paper as well. So I just wanted to conclude quickly and say that LRO is the gift that keeps on giving. We are, as I said, planning is underway for the 4th extended mission, possibly due next year, potentially the year after. We are evaluating how we can change our orbit to enable new and exciting science. And as we'll see in the rest of this session, we're looking forward to cooperating with any future mission of any size, whether it's a CubeSat, landed mission, what have you. We're really excited to be joined in lunar space by some company. Now, I have, by my clock, about 30 seconds left. I won't go too much into talking about the Eclipse, but I did want to highlight this product that we talked about the other day, yesterday, showing the path of totality as it crisscrosses the country. Pays special attention to what happens when the shadow passes over mountains. You can see the rippling effect, which is caused by the Earth's topography changing the location of the path of totality. And again, each of these sides of the shadow are caused by basically these spotlights, these lunar valleys along the limb that shine onto the surface of the Earth. So if you're in the path of totality and you get to experience this, we can actually trace, and I'm going to skip forward, which valley is you're seeing the light through. So at some point I'll have to sit down and figure that out. This is just an example of what you would see in a assumption of a spherical moon and a spherical Earth is the red circle, and then if you take into account the topography of the Earth and the moon, you get these various other shapes. So this wobbling one is accounting for both the shape of the Earth and the moon, and you can see that the shift is in some places kilometers different from our assumptions. And so on August 21st, everyone will get to bask in the glory of the shadow of the moon. With that, I will end. Thank you very much.